we've got three derivatives here that we need to find. The first one, we have e to the x minus 2 to the x, the whole thing being raised to the fifth power. This is a perfect example of a function living inside of another function. So this is the baby, and the mama is x to the fifth power. Raising it to the fifth power is the mama. So the way that works, we take the derivative of the mama, which is our chain rule, 5. If it was x to the fifth, the derivative would be 5x to the fourth. 5, and you leave the baby alone, times, now we need to take the derivative of the baby. Okay? So we have 5 times e to the x minus 2 to the x, all raised to the fourth power, times the derivative of e to the x minus 2 to the x. And fortunately, we know how to take those derivatives. We have derivative of e to the x is e to the x, minus the derivative of 2 to the x is 2 to the x times the natural log of 2. And we're done with that one. Hooray! All right, p of x, the square root of the sine of e of x. E to the x is the baby. That baby is inside of the sine, because remember, how did we say it? We said it's the sine of e to the x. E to the x is the function inside of the sine. But oh my goodness, all of that is inside the square root. So the sine is the mama, and the square root is the big mama. So what do? If I want to take that derivative, p prime is the derivative of the square root is 1 over 2 square root. Square root of what? Square root of big mama's baby. We just leave the baby alone. Times. Now we take the derivative of the sine of e to the x. Okay. Breathe. Derivative of the sine of e to the x. Now we're ready to take the derivative of sine, which is cosine e to the x, times the derivative of e to the x. How do we take the derivative of e to the x? Derivative of e to the x is e to the x. When we put all this together, we have 1 over 2 square root sine of e to the x times cosine of e to the x times e to the x. And I would stop there. Okay. One more problem. We have e to the x over cosine of x, the whole thing being squared. I think it's pretty clear that the square is the mama. The baby is the whole e to the x over cosine of x. And I think some of you already know what I'm going to say. This is a quotient rule. In order to take the derivative, in order to find L prime, you take the derivative of the mama, which is 2 times, it would be 2 times x. So 2 times e to the x over cosine of x times the derivative of e to the x over cosine of x. You have to use your quotient rule here. So the quotient rule, let's just rewrite everything else. 2 times e to the x over cosine of x times, quotient rule says we take cosine of x times derivative of the numerator minus the numerator times the derivative of the denominator. Derivative of cosine is negative sine over cosine of x squared. You could clean your answer up a little bit if you'd like. Negative e to the x times negative sine of x makes that a positive. You've got an e to the x showing up in both terms. You could factor that out if you would like. Kind of running out of space here, that's always bad. So let's see what we can do. We could make this final answer 2 e to the x over cosine of x times, factor out that e to the x, leaving you cosine of x plus the sine of x all over cosine of x, the whole thing squared. If you want to go further, you could multiply out the numerator. 2 times e to the x times e to the x is the same as 2e to the 2x times cosine plus sine. In the denominator, you have a cosine of x times cosine of x squared. Yep, you guessed it, cosine of x cubed. Okay. I don't worry too much about this final simplification. I do want to make sure that you are comfortable, that we're all comfortable with this is a chain rule problem. The baby is going to involve a quotient rule. The mama is just x squared. So it's 2 times the baby times the derivative of the baby, and then we use our quotient rule and we simplify as far as we can. All right. Recenter that. The last derivative rule that we talked about is how we handle inverse functions. This is a helpful technique, especially for some of the more complex functions that we're going to look at later on. For right now, if it's just a matter of when you see the word inverses, when you see that we're taking derivatives of inverses, you know this formula, you have it memorized, that's probably going to be okay. So if f and g are inverses, then the relationship is that the derivative of g is equal to 1 over f prime of g of x. And we went through, we derived this in class. We started with the relationship that since the functions are inverses, the composition relationship is true. We took the derivative on the left involves a chain rule. So f prime of g of x times g prime is equal to 1. If I want to solve it for g prime, we're going to divide. So g prime equals 1 over f prime of g of x. And that's where this bad boy comes from. Usually when you're solving a problem, f of x will be the known function. They either tell you exactly what the function is, or they've given you information, or there's some way to go about finding it, and g of x is the one that you really want to know. And it's this inverse relationship that gives you the information that you need. So let's look at a pretty straightforward example. F is defined by the function x cubed plus x. G of x equals f inverse of x. So this tells me there's that inverse relationship. F of 1 is equal to 2. They've given me more information about f, the function f. And I want to find g prime of 2. Well, we know the relationship g prime is equal to 1 over f prime of g of x. So that would mean that g prime of 2 is equal to 1 over f prime of g of 2. In order to finish this off, I need to know what g of 2 is. But if I look at this problem, I don't actually see it written out. I don't see g of 2 equals some number written down somewhere. But if you pay attention to the fact that f and g are inverses, this is like algebra 2 information. Saying that g of 2 is equal to some number is the same as saying that f of that number is equal to 2. That's that inverse relationship. If g of 2 is equal to some number, then f of that number is equal to 2. So what's g of 2 equal to? Here it is. Since f of 1 is equal to 2, that means g of 2 is equal to 1. So we can go back and we say that we've got 1 over f prime g of 2 is the same as 1 over f prime of 1. How do I find f prime of 1? I'm going to go back to my original function. I'm going to take the derivative over here. I'm going to replace the x by 1. The derivative of f of x is 3x squared plus 1. If I find f prime of 1, I should get 4. And our final answer is 1/4. So that's what g prime of 2 is. If you are feeling pretty good with that, great. This next example is a much more challenging one. I think it's fun, it's exciting, it's not something that we had a lot of time to focus on this year. It's also not something that shows up a tremendous amount on the AP exam, but this is an example of why inverse functions are so powerful. And I'm going to go through this one in the next few minutes. If you're feeling a little bit overwhelmed with inverse functions, feel free to stop the video now. We'll call this the director's cut. So, we're being asked to find the derivative of arc cosine of x. That's the function that we're after. So, if we're going to find the derivative of arc cosine, that's the derivative that we want, but I don't know how to find the derivative right now. But I do know that if I consider f of x, if I look at f of x equals cosine, then the arc cosine is actually the inverse. And that's what we typically call g. And so because cosine and arc cosine have this reciprocal relationship, then it means that the derivative of arc cosine, will be equal to 1 over f prime of g of x. G of x is what we're calling our arc cosine, so I need 1 over f prime of arc cosine. Well, if f is the cosine, the derivative of cosine is negative sine, so I need 1 over negative sine of the arc cosine of x. Let's stop and think through that again. We wanted to find the derivative of the arc cosine function. This is the function I want, but I don't know how to do it, so I'm going to call that g. From pre-calculus, we know that arc cosine is the inverse of the cosine function. So we have this relationship. Because of this relationship, it must be true then that g prime is equal to 1 over f prime of g of x. So that means that it's 1 over f prime of arc cosine. If f is cosine, f prime is negative sine. And so we've got this. And that's great, but that's not going to be our final answer. In order to get to our final answer, we need to think back to the unit circle. When I say arc cosine of x, what I'm really asking for, this is an angle. And I'm saying what angle has a cosine equal to x that allows me to draw a right triangle. That's my angle. If the cosine is equal to x, the cosine is the adjacent side over the hypotenuse. So I'm going to label the adjacent side x, the hypotenuse 1. What I'm missing is the opposite side. But thanks to the Pythagorean theorem, we can say that x squared plus the side we don't know squared equals 1 squared. So the side I don't know squared must be 1 minus x squared. So the side I don't know is the square root of 1 minus x squared. There it is, square root of 1 minus x squared. Good golly, even that's not the final answer. I told you this one was tricky. The derivative that we're looking for is 1 over negative sine of the arc cosine. But that's just an angle. How do I find the sine of this angle? I take the opposite over the hypotenuse. So the derivative I'm looking for is 1 over negative square root of 1 minus x squared. There it is in all of its glory. The derivative of the arc cosine is negative 1 over the square root of 1 minus x squared. And we could go through and develop similar derivative rules for arc sine, arc tangent. We could do all of them. Don't worry about this too